G'day everybody and welcome back to my channel. So I'm continuing on with this power supply prototype. It's a prototype, but it's a prototype that I'm going to end up keeping and using probably for the rest of my life, you know what I mean? I'm going to make all the boards up properly and it's going to be a lot more refined and neat when I make the finished version. But the thing is, originally I was actually designing this on breadboard, and especially when I started doing stuff like this, constant current circuitry with multiple op amps. There's still 2 op amps missing off there. They're OPO7, so they're only single op amps. But the resistance in breadboard tracks, like, you just can't do precision circuitry like that. So I find it's easier to etch boards like this and not drill the holes through them, just solder the components from the top like this. And I can just tack things on and off and adjust values that way. It's like, it's neater than, you know, what do you call it, dead bug style, the way Bob Pease used to build stuff and people like that, you know, when they were prototyping. It's not all just like a bunch of components twisted together or soldered together, but, you know, at least it's solid. You know, I mean, this ain't going nowhere, you know what I mean? And I don't have to worry about, what do you call it? You know, high resistance connections and all that sort of jazz, you know? Anyway, you're all going to laugh at me. I ended up still having to do a little bit more work to 2 of the panel meters. Turns out 2 of the caps I put back in with the wrong value. They were actually supposed to be 1 microfarad, not 100 nano, so I corrected that. Also, the trim pots, they're just not good enough. I'm going to end up putting 25 turn trim pots on there. But, you know, I probably won't bore you with a video on that. I'll just include like an update saying, hey, I've done it, and show you in another video, just as I've just spoken about it just now for a brief moment. But yeah. What I'm going to be doing today, so I've got this little main wall switcher. Nothing wrong with that. I've got no problems with this. But it spews out AMI radiation, mainly from the transformer and switching device area, obviously. And it all comes into the output of this power supply, this cable here, and the reference board. And as you can imagine, coming out of the reference board goes into basically what's essentially a voltage comparator, which controls the series pass element, and it ends up on the front terminals. Not a lot, but a portion of the noise. So I have to do something about that. I'm not going to change the design of the supply, so to speak. I think I did end up adding output capacitance to it, because this supply, it's got a little like a pi filter here. It's got some output capacitors with a coil inductor in between them, a little current shunt, rectifier there. There's no little ceramic caps on the back. There's just that one there, which is part of feedback circuitry, I think, or a snubber. No, it's part of a snubber. So, and then there's this little common, I can't clearly see how that's wound. Hold on. I think it's a common mode choke, but yeah, common mode choke. That's a common mode choke. There's no high frequency suppression really on it, other than what they've done inductively. So yeah, I'll probably add a little bit on just on the outputs, like, you know, external to it, just in the, you know, stick some capacitors in there with the wires that go into it basically. But that's not what's going to fix the noise problem. That's just going to stop noise getting into any other circuitry that I run off of it. What I'm going to do, I'm going to experiment with different materials. That's what the purpose of this video is going to be. What I'm going to do is I'm going to just slide this in here, give it its power. We don't need to worry about putting a load on it. It probably actually does spew out more noise under load, so you know what, I will hook up the load. It's probably the wisest thing to do. So yeah, hook up power and load to it, and ground, because don't forget there's noise suppression inside it, and I'm not just talking about common mode circuitry on the input, but you know, sometimes there's separate windings in the transformer that go to neutral or ground or back to a capacitor that feeds back into it somewhere, and a lot of this noise gets suppressed to ground via internal circuitry. So we'll hook up the ground, the power, the load, and then I'll hold it over here where it gets mounted. It gets mounted, these two screws I've put to go through the case, you go in the back of it. It sits right exactly there, like that basically, with the front cover on it. That's what it is, a 15 volt, 1.34 amp. I can't remember, I've got the voltage set to, it might be a bit higher, might be a bit lower, but anyway. The reason I needed a little bit higher is because I wanted to do all the fan circuitry off one little switcher. One fan I wanted to run just at 12 volts all the time, this little miniature fan that's on the heatsink for the rectifier at the back. But the other fan for the, what do you call it? As you can probably see, there's been multiple iterations of this. Series pass device heatsink. That has a fan speed controller. So the fan speed controller, you know, due to the nature of there being diode drops and in transistors and parts of the circuitry, you know, if I was to only feed it 12 volts, the fan could never power up to 12 volts. And I think I run the fan at something like 13.5 volts or something at full. This is why I need to put a bigger heatsink in there, but that'll be the next thing that I do after this, incidentally. And then I think there's one or two more things I wanted to do, and then I'm on to the constant current circuitry. Anyway, and ovenizing a bit of circuitry. Anyways, before I get carried away going on about stuff that I'm not doing now, by setting this at 15 volts, it gives the headroom for the regulator to, you know, power the fan in between, say, whatever its lowest speed is that it'll turn over at reliably, like 6 volts or whatever, up to 13.5 depending on the temperature of the heatsink, and allows me to power a regulator for the other fan to run at 12 volts off the one supply. So that's why I'm using that. That circuitry is not referenced to any of the other circuitry in here, so that's why I'm not worried about how much noise it puts out so much. You know, it's in terms of the outputs, I mean, but not in terms of magnetically radiated noise. That is a problem, because that is, well, that's the problem we've got to deal with. So what I'm going to do, I've got a scope probe still hooked up to the output. It's still not hooked up in the best spot, so there's a little bit extra noise on the output compared to what there actually is, but that's okay. I can see through that. We're gonna just look at the scope screen. First I'll, you know, like I said, power this, earth it, load it, move it over the area in question, and you'll see what happens to the scope, which is looking at the output of the supply. Then we're gonna try and put stuff in there like a single-sided sheet of copper PCB. See what difference that makes. Then try grounding it, see what difference that makes. Then try all different things, you know. Maybe a snubber between the sheet and ground. Maybe a double-sided sheet of circuit board with both sides grounded or snubbered to ground. Or we're just going to see what works to shield it, you know. So that's the purpose of this video. So without further ado, I'm going to set up a few things and I'll be back. Just before I go and do all this stuff with the power supply, I just wanted to do a quick measurement. I've got it set 20 volts, 5 amps on the load bank, and I'm just having a look at the temperatures on the transistors. I've got the fan controller circuitry all powered up. Anyway, I'm just watching the temperature rise. I might not need a bigger heatsink, we'll see. I've just got to soak test it. I might increase those emitter resistors to 0.22 ohm instead of 0.1. I don't really want to do that. I only do it if I have to. Transistors are pretty evenly mounted on the heatsink side by side. They're very well matched. They've got base resistors. We'll see what happens. Anyway, I'll get back to you and report on how this goes. I might end up being able to leave that heatsink in there and not have to change anything. I'll still change the transistors because I just found that they were my last old school 2SC5200s from like the 90s, and I just found the two 2SA 1943s that were matched with that set for an amp, so I want to keep them, and I'll put some new TT C5200s that are still good, that are on those heat sinks from one of my amp builds in here, and use the new bags of them, the 2SC5200s and 2SA 1943s for my amp build that's coming up. Anyway, 64 degrees is actually pretty good, considering at most these transistors will be dissipating about 40 watts around that area. Maybe 45 at the worst case scenario. It's uncomfortable to hold my finger on there, but it's not. I'm pretty happy. I don't think we're going to have to put a bit bigger heatsink in there after all. The reason I came to that conclusion... Sorry about that. The reason I came to that conclusion at all was because, I don't know, one time I loaded up to like 5 amps and I felt the heatsink or something and it just felt too hot to me, but no, it's not. I'm just gonna wind the relay down one click. Let's see what that does to the temperature. No, that's dropping off straight away. Okay, back up. I think 20 volts is the worst it can get. You gotta understand, with a linear supply, it's not the heatsink gets the hottest when it's up at full voltage, because the series pass transistor's trying to drop, you know, essentially a crap ton of voltage. Well, the transformer's got so many taps, so like when it's on the 38 volt tap, for example, and it's set at 20 volts, that series pass transistor's trying to drop all that excess voltage. So whatever that voltage is across the transistor times the current running through it is the wattage it's trying to dissipate. So your worst spot on a switching power, on a linear power supply, the worst temperature spot's going to be right in the middle of the highest voltage, if that makes sense. If the highest voltage is 30 on that tap, set it to 15 volts, load it at the highest current, measure the temperature of the transistors. That's what I'm trying to get at. I'm literally sitting around 62, 63, 64 degrees. Maybe going up to 65. We'll see. I got a half a volt difference on the tap changing circuit, so it'll turn up to the next tap at 20 volts, but it won't turn back down until 19.5. Even though, you know, the voltage doesn't even deflect by a millivolt on the output, just in case there was, say, some sort of load or it presented some really sharp current pulses, something like that. You don't want your relays to start chattering. There's also a few other interesting techniques in there to make sure that things can't go like sour like that, you know, like two relays coming on at the same time, for example, stuff like that. Anyway, we're not working on the relay board. That's well and truly designed and has stood the test of time. That relay board, the switches between the taps in there, has been working for years. I had a problem with it one time, that's why the cover's off that one last relay that you can see me turning on and off, so you can see the arc. Yeah, well, I am literally not going past 64 degrees, so I'm amazed. I thought I was going to have to raise the emitter resistance, put a bigger heatsink in there. Well, that is bloody hot. Just making sure my probe's actually like touching the transistor. Just gonna try and hold it. I've put some, not thermal paste, but thermal paste glue on here. I'm just still not seeing anything. So you guys can see what's going on too. That's the temperature of one of the transistors, and I can put my finger on both of them. I can tell you they're both the same temperature. They're both literally the same HFE, almost the same VBE, they're the same batch, same everything. They're mounted next to each other on the same heatsink, not on top of each other. Emitter resistors, base resistors are matched. Like, you can't get them any closer. I can guarantee they're both doing the same thing. So, this is wonderful news, and this has been running like this for a long time. Like everything. Oh, there goes my thermocouple. Well, that's alright, I was about to take that out anyway. I'm content. I'm going to say that I don't need to worry. That's wonderful. That's one less job to do on here. All I've got to do is ovenize some components, install this power supply. Oh, I just need to shield it. It's already installed. By the way, the fan runs at 15 volts at full speed, which is actually surprisingly alright for some fans, and I know which ones are alright because I've tested them. I've run some of these little DC ball bearing fans for like literally like years and years since I was young, and I still have them. Others won't go beyond 12, 13 volts without popping, it just depends. These ones handle it, so I've put one in there. It's a 20 or 25 milliamp fan. 20 milliamp fan. Comes from J-Car, yes. The J-Car ones will take 15 volts. They're one of the good ones in terms of voltage. They are technically 12 volt fans, but they don't overheat. They've got, some of them have got different driver circuitry. The way they interface with the little Hall sensor sort of IC. Some use a different part. Some use different designs like transistors to switch the coils, FETs. It kind of just depends on what design you've got as to how much it will heat up, and also the coil winding itself. But I don't think it's usually the coil that's a problem with the extra couple of volts. I think it's the circuitry. In my own experience, I've found a lot of them handle 15 volts without getting warm or anything like that, heating up crazy. Alright. Yeah, I'm happy with that. Alright. I'm going to reset the camera up now, and I'm going to show you what happens when I put this in there in terms of the noise that it injects into the circuit. Let me just wind this all the way up to 30 volts. Let's show you something. And yes, this is running at 5 amps. Just for those that are wondering, if I really wanted to get that 450 watts, all I got to do is just put it in 4Y sense mode, and it will deduct the drop off the cable. I don't know why I don't just do that, eh? Which cable switch? That's my sense. I can't be bothered. It's good enough. Anyway, I'm going to reset the camera up now on the tripod so that we can stick this, set the scope up, look at the scope and all that, and yeah. See, off a power supply, a load bank, which puts out that much noise, it's not funny. That's why this capacitor's here. My power supply is still only putting out 233 microvolts of noise. The peak to peak figure is higher because of the spikes from the load bank and because my probe's in a shit location. That's how quiet this supply is. It's wonderful like that. I'll stop recording. Alright, what I'm going to do, because if I put the camera back here so you can see the power supply and the scope, I'll try it first, but I don't think you're going to be able to see the waveform enough. Let's see. Maybe I'll turn the voltage all the way down, because it's noisier at the top end than the bottom end. The reason I'm also very concerned about noise on my build is because one thing about power supply builds is as you slowly add more circuitry, it introduces more noise pathways. So considering I've only got, like half of it built, it's potentially going to go up by at least double in noise. So I want to keep everything down as much as I can. Yeah, that's really odd. I could have sworn that this was causing me problems before. You know what? Maybe because I've got my scope connected to a poor spot, I can't see it through the noise that's already there on the screen. Well, let's just see. Yeah. Okay, so you can see what I'm saying. When I put it right in there, you know, it does have an effect, but actually seems quieter there. Let me just put my insulated screwdriver away. One sec. Let me just disconnect power to it so it's not switching for a sec. Right, we're reading about 67 microvolts RMS. Plug it in. With it out there, we've got 70 microvolts RMS. Let me just screw this active wire in, it's sparking around. With it where I want it. Back down to 64. That's odd. You know what I might have done? Don't ask me. I might have tried, I think this is what I did. Man, you know what? I might have just gotten out of 2 bits of work. This is awesome. This is truly awesome. I've got a funny feeling I wired the panel meter up to this 7812 regulator, which is supplied off of this, and the panel meter must have been spewing the switching noise from this, and the you know, I'm referring to the display, multiplex display noise from that, all back in the power supply. Through wiring, not electromagnetically. Huh. Well, I'm just going to quickly mount this back in where it goes, just in case there is more to this. And you know, like when it, I don't know, maybe when it's screwed to the case, I don't know this. This is just a theory I've just come up with. Maybe this plastic is sort of made out of some sort of, it's got some sort of slight carbon added to it that makes it a shield. But when it's screwed to metal, it transfers the radiation into the metal. I don't know. I'm just speculating. I'm leaning more. Where are my magnets? I'm leaning more towards the point that I just said. I think what's going on. Oh, God. No. Bloody neodymium magnets. Oh, God. Just give me a magnet. Are you shitting me? It's still a magnet. Wait. That's not a magnet? Oh, no. I just picked up something I thought was a magnet. It's not a magnet. That was random. Well, this is a magnet. Let's get these screws in the holes. Seem to have just lost a screw. Oh no, it's here. How do I have it? Do I have it this way or this way? Because it's might have something to do with the case. It might have some. I don't see how, because if it is, it'd be just going to ground because the case it's being screwed into is shielded. So I don't know. Maybe it's something to do with where it's mounted, because now I'm putting it in here, I'm realizing it was closer to the transformer. So maybe somehow it's coupling into one of the transformer windings. I don't know. But what I know is that this was definitely an issue before. And as you could see, when I do hold it over the reference board, it does spew out noise, and you can see it, but it's not doing it over here. That's originally why I decided to mount it over here, because I didn't want to put it over sensitive circuitry. If you're going to mount a switching supply in a product, keep it away from high impedance circuitry and sensitive circuitry. What? Well, you know what? It does go that way. Okay. I might have just answered my own question. Maybe because it's upside down. What the bloody hell? Maybe because it's upside down, that's allowing the transformer to, let's just see. Yeah, we're up a little bit. You can see that there is more noise there. That's interesting. You know what I think the solution is? Turn it around. Wow, okay. That's all I've got to do. Well, I'm not going to bore you guys with a video on that, because as you saw, when that was around the other way and held there, that was way smaller. So I'm just going to turn it around. I mean, you can't ask for an easier fix than that, can you? Alright, well, I think I'll leave that video here, because I was going to shield this, like I said, which it seems we don't need to really worry about that now. And the other thing I was going to do is put the transistors, slightly different transistors, but basically the same. Same transistor in a smaller package, basically, just slightly smaller. I was going to put them on a bigger heatsink that sort of stuck out the back. And I'm happy to run two 2SC 5200s in those huge packages, dissipating a maximum of about 40 watts each. Maximum. It's probably even less than that. That's fine. So, yeah. I mean, the two transistors have got 5 amps going through them with a maximum, say 30 volt drop at the most. They could have about a bit more wattage than that going through them at some point. I don't know, it's probably closer to a 20 volt drop. Oh, hold on. Make sure there's nothing that's going to short out on that, something like that. Alright, let's get my load here. Oh, fuck. Oh, the capacitor was charging up when my power supply hadn't started up yet. I see what happened. I thought something was wrong. Okay, so Let me put 5 amps on here first. Turn the load on. Let's look. Film collector. Something doesn't seem right. 18 volts. You hear the fan starting up? Because that's the hottest it runs, so it'll come on fairly quickly. If it's only running warm, the fans run slower, and if it doesn't need it at all, they turn off. That's the way I designed it. I'll turn the light off now. So yeah, about 40-45 watts, something like that. Well, that's great. So I'm going to turn that around, mount that the other way around now. Leave the outputs how they are with the 0.1 ohm emitter resistors and the heatsink and fan set up like that. I'm going to move on to the ovenizing of these components. Basically, my whole idea behind the design of this power supply, laugh at me if you want, I wanted to test the theory out and see how plausible it was. I wanted to use some questionably ancient techniques with some new modern day techniques sort of mashed together, but also using the KISS approach, so keep it simple stupid. So like for example, the whole voltage circuit, the constant voltage circuit, it comprises of a regulator that feeds two transistors in a regulator that feeds the drop resistor to a comparator transistor, which has its emitter is tied to the output, negative, and its base is looking at a super stable reference that's powered by a super stable power supply, and it's looking at that reference in between the positive output and the base, and the reference is adjustable. The reference is an ATL431BQ board with a transistor to buffer it, going into a 10-turn pot, and the power supply is my own switching power supply with a whole load of extra stuff added to it to make it super stable over a wide range of input voltages and very quiet. The tap changing board, it's an LM324 op amp, but there's a whole load of Zener diodes and JFETs in there around the place too that do interesting things to make the switching foolproof, so to speak, putting it in layman's terms. The current shunt, I built that myself out of a bit of Constantine wire. Transformer was harvested out of MP3840 Gaycar 5 amp 30 volt power supply. It's an interesting one, and I wanted to prove to myself that I could pull it off, and so far I've had every result that I wanted to get out of it, I've accomplished, so I've decided just to keep going with it. Like I said, these things I find fun, I enjoy it, so that's why I do it. Plus then I also get something that I get to use, for the rest of my life, so that's pretty cool too. Anyway, I'm going to turn this off before that goes somewhere and goes bang. I didn't get zapped, the circuit board landed on my hand and I got quick reflexes, so I didn't want to get zapped, so I sort of moved my hand out the way very quickly. Alright, well, I'm going to mount this thing in a different orientation now, which means just drilling one hole in a different spot in this box basically. Actually, that might not work. I don't know if I can get this board to go in both ways or not. Definitely goes in that way. There are runners on each side. What have they done? Oh, I see. The bottom two runners it just, oh what? It's just half the runner's a little bit smaller on one side. I could jam that in there. That's just a defect in the packaging. It's not even intentionally made like that. No, not without damaging it. I have to show that on camera. You see all the four runners are basically the same size. Bottom two are a little bit smaller, but at the back of that one, let me get a light. At the back of this one runner, the actual runner itself just slowly tapers out and gets smaller as it goes in there. I don't think I'm going to be able to get this. I tried. Sorry. Anyway, I'll work out how to get that around the other way. Alright, well, that concludes that for this video. That's the answer to like my switching noise solution, and I do not have to make a bigger heatsink, so that's great. For those that are wondering why there's a bit of Captain tape on top of the heatsink, I hate mounting transistors on a heatsink with some sort of thermal insulator like mica or sill pads. If I'm going to do it, I like mica better, but obviously I'd rather just mount them direct to the heatsink, make it the surface as flat as I can, put thermal compounds on there and bolt them up. That's what I've done, so therefore the heatsink's at the same voltage as the collector, which is, I can't think. Ooh, can't believe it. That was a miracle that didn't touch nothing. As I was saying, the collector voltage can be as high as 51 volts. So almost 52 volts. So yeah, I mounted Captain tape on it and an insulating sheet underneath it so it cannot make contact with the frame. I cut out this notch here in the frame. It's mounted to the fan, which is plastic, and then the fan screwed to the back, so it's literally fixed, isolated from the frame. Otherwise the frame would then be 52 volts, and even if that didn't present a danger, unless it came in contact with other equipment, it would completely screw up the noise of the supply and other things too. So yeah, that'd be really, really dangerous, and just like, it would just act as a giant antenna basically. Alright, that's all for now. I'll see you guys in the next one.